All right, Patriots, welcome back. I am Mr. Love, a.k.a. the Math Patriot, bringing you another fun and exciting lesson from the wide and wonderful world of high school geometry. We're moving on to Unit 2 today. We just finished up our basics of geometry, talking about points, lines, planes, angles, all that sort of stuff. And now we're moving on to our inductive reasoning, conjectures, conditional statements, etc. Later on, we'll be moving on to proofs, but for now, we're just getting on to some of the base logic stuff. By the way, I'm coming to you recording from a new class they've never recorded before, so if they don't ever give any input, I'm sorry, we'll make it work. All right. Hey, guys, say hi.
Hi.
Hey. All right. By the way, y'all are the first class I've let do that, so hey, you're special. Okay.
Yes, I am.
No, not special ed.
I didn't mean that.
Some of you. I don't know. Okay. All right. Now, moving on. First off, inductive versus deductive reasoning. Now, deductive reasoning is whenever you are using accepted facts, rules, definitions, etc. to make a conclusion. So, the vast majority of the things that you have done in a math class have been deductive. We tell you the rule, and therefore you repeat the rule. Algebra, right? We tell you how to solve for x, you keep on solving for x over and over again. All right? Our example here, the rule you're given, all humans are mammals. You're also taking a fact, John is a human, and you're putting those together to come up with the idea that John therefore is a human mammal. Okay. Inductive reasoning is where you're using reasoning based on an observed pattern, something that you have watched occur. Okay? So, for example, you guys have been taught about the theory of gravity, right? You know that what goes up must come down, and you've been taught that. So if somebody were to hold a pencil in the air and you look at it and say, hey, I know the rule of gravity. It says that if he drops it, that thing is going to fall. Well, since you're using a rule, that's deductive. Now, what about Sir Isaac Newton himself sitting under that tree? I don't know if you can actually believe that story is true. Some people have told me otherwise. But what about him sitting under the tree with the apple falling on his head? Induction or deduction?
Induction.
Why the induction?
Because it's not like an accepted fact of gravity yet. It's simply something that he just observed.
Right, because at that time he observed it and he was coming up with it on his own. All right? So one of the places where you do use induction in math class is to observe patterns and move forward. So if we look at this pattern, what pattern are you seeing here in 1, 3, 5, 7, and 9? Okay, so we're adding 2 to each element. So add 2, we're going to be 11 and then 13. Yay. All right. So now a conjecture is an educated guess based on known information. Now, in science class, you may have seen something similar to this for the word hypothesis. We're going to use the word hypothesis in a very specific way later on today. Okay, so conjecture is where you come up with a guess about the pattern. Now, let's go ahead and complete this pattern here, okay? What's our guess about the pattern going on here?
Odd numbers.
Odd numbers, okay? Odd numbers, okay? So we're just writing the odd numbers. Therefore, the next items would be 9 and 11. Same pattern as the previous slide, right? Counterexample is an example, and when I say example, I mean literally like x equals 4 or this thing happened, okay? Give me a specific example that shows the conjecture is false. So we're going to give a counterexample for this conjecture right here. And now, I wouldn't expect most people to come up with this, but notice there's a difference between this one that starts at 1 and goes to 9, and this one that starts at 3 and goes to 7. Okay? In particular, the 1 and the 9. All right? So what if instead of the pattern 3, 5, 7, 11, it was actually supposed to be 3, 5, 7, 11, 13, 17. What if this was actually a list of prime numbers? Would that still fit the original condition?
Yeah. Yes.
Yes. Now, it would actually be prime numbers starting with 3 because 2 is our first prime. Okay? But that's our example to show that maybe, just maybe, our conjecture was not true. Okay? And then this, our prime numbers, is the counterexample because it's the example that proves our conjecture was false. And by the way, if you can come up with a single counterexample, then something is considered false in mathematics. Okay? It's not that thing of, well, it's usually false, but there's this one kind of sort of weird edge fringe case that makes it true. And so I'm going to say the thing is true. No, it's actually the exact opposite. If it's usually true and there's this one bizarre edge fringe case that just happens to make it false, then the entire thing is considered false. Okay? In mathematics, it is only true if it is always true, without any exception. All right, here we go. Write a conjecture that describes the pattern in the sequence. Then we're going to use our pattern to find the next item. So what are we actually doing to get from item 1 to item 2?
Adding 3
Okay, it looks like we're adding this piece here and this piece here, right? So we're going to add 2 shaded rhombi. I heard somebody say diamonds. I don't like the word diamond in geometry. Rhombus is actually a better word, and rhombi is plural for rhombus. Also, rhombuses is an accepted plural. Not 2 shaded rhombi, and 1 unshaded rhombus on the right. And so for adding the next one in the sequence, instead of drawing a whole bunch of extra ones, I'm just going to draw it in. And remember, we always pretend that my drawings are perfect. Yes, thank you. There is no pretending. My drawings are always perfect. Yes, please add that into yours as well, because that way you have the notes for later. All right, anybody watching this online, sorry, giving my local class a second to write things down. All right. Moving on. Example 2. Write a conjecture that describes this pattern and then give me the next item. So what is our next, or what's our pattern here?
+3.
+3. I'm going to say you're going to add 3 to the previous item. Now that previous item part might sound like a little bit of overkill, but there are certain patterns where it like alternates. You do like alternate things to do from one item to the next, and you're actually going back 2 or 3 items to figure it out. So I'm just going to go ahead and say specifically the next one, or the previous one. All right, so if I add 3, my next item is going to be 11. All right. That one doesn't require as much writing. We're going to go ahead and go on. This one is interesting. Any suggestions on a pattern you're seeing there? All right, go ahead.
So you go back to the one before the previous one and subtract 1 from it.
Go back to the one before the previous and subtract 1 from it?
Yeah.
Okay, that's viable, but again, that I would like to come up with a rule that even incorporates why the fractions are there in some but not in others. Because they wanted to, yeah, that is correct, but it doesn't work for here.
It's -1/2.
Okay, you're right, it's -1/2, but that's only part of the story. Why are some of them fractions and some of them not?
Because it alternates.
It alternates? In theory, yes, but there's another piece I can put in there to make it all one whole nice rule. Yes?
Subtracting 2 the whole subtracting 2 and fraction 11.
Okay, subtracting 2 from the numerator, then dividing by 2. Yes, you're right. Okay, we're getting there. Here's the way of incorporating the whole thing. what you're going to do is subtract 1/2 from the previous item. And now, I was going to go ahead and point this out, that this is actually 12 halves, right? This is also 10 halves, and this is 8 halves. So the reason that the 12 halves is written as 6 is because it's a reduced fraction, right? 11 halves is also a reduced fraction. So we're going to just subtract 1/2 and then reduce the fraction. Now, knowing that, what's my next item? 8 halves minus 1/2 is 7/2. Reduce the fraction 7/2, and we're left with 7/2. All right?
Why are only some of them fractions?
Because we reduced the fraction. That's why some of them are fractions. Because 12 halves reduced is 6. 10 halves reduced is 4, or is 5. All right. Make a conjecture about the geometric relationship. A, B, and C are collinear. So let's go ahead and draw the picture here. Pictures are always worth 1,000 words. A, B, and C are collinear. Also be careful when you draw a picture. Don't assume that the way you drew it is the only way it can be drawn. Because, for example, for A, B, and C to be collinear, it's also possible that I had this, right? B could also have been over here. Right? So my point is there's different variations on this. You got to consider that when you're looking for truth of things. All right. And D is between B and C. Now, I don't need that for this one. I just wanted to point that out. So D is between B and C. Now we know the word between means that there is going to be collinear as well. So we're going to put that in there. And D is there. What conjecture can I make about all 4 points? Yeah. All 4 points are collinear. There's my conjecture. I'm sorry, what? Collinear, all on the same line. Collinear is all points are on the same line. All right, example 5. Angles 1, 2, 3, and 4 form 4 linear pairs. Now the picture is definitely needed on this one. The real trick on this one is how do you draw it? As a square? Well, if we draw a square, 1, 2, 3, and 4, does that make any linear pairs? No, because a linear pair is going to look like that, right? 2 angles together to make a line. So square can't work. Okay, an X shape. All right, 1, 2, 3, and 4. Well, would that make 4 linear pairs? There's 1 pair, there's 2 pairs, there's 3 pairs, and there's 4. Yeah, we got 4 linear pairs. All right. Now, what conclusion or conjecture can I make based on that picture? There's a couple that I would take. Go ahead.
2 sets of vertical angles.
Okay, it creates 2 sets of vertical angles. I like that. I'm going to put exist there. Okay. The place you could go too far on that is saying that 1 and 3 are vertical angles. The reason that wouldn't work is because it's entirely possible that like I had just named them differently. Now 1 and 3 are not vertical. Okay, so don't go so far as naming them. Another thing you could say is all angles have the same vertex. They all share a vertex. That would also work. There's probably a couple others, but I'm not going to go too far into it. Not just, I mean, we got other things we're doing too. But it is this type of thing all day, yes. For the entire lesson. All right, next up. If angle ABC and angle CBD form a linear pair, well, first off, what's that going to look like? Yeah. Sorry, y'all can't see this. They were drawing on their papers for me. Boom, linear pair. Then angle ABC is congruent to angle CBD. Oh, sorry, I forgot to read on these. Determine if they're true, and if they're false, give a counterexample. All right, so is it true that angle ABC is congruent to CBD?
No.
Okay, no. Give me a counterexample. And a specific set of numbers will work for a counterexample. Okay, give me a set of numbers that would make this not true.
120 and 60.
Yeah, 120. So if this is 120 degrees and this is 60 degrees, they're not congruent, right? So that's my counterexample. In this case, the entire picture is my counterexample. Now, here's what's important there. The counterexample must satisfy the if portion. We'll talk more about the if portion in a second. But ABC and CBD form a linear pair. Do these two form a linear pair? Yes, they do. If they did not form a linear pair, you could not use them as a counterexample. Okay? They must meet the first condition and disprove the second. All right. AB, BC, and AC are congruent, then AB and AC are collinear. Now, drawing this one is the hardest part of it. We're going to see if it's true, and if not, give a counterexample. How could I begin approaching this one? Okay, put them all on a line, okay? A, B, and C. All right, so we got A, B, and C all in a straight line. And then let's see. AB is congruent to AC. I'm sorry. AB is congruent to BC. But that also must be congruent to AC. Now, can I do that? Where this distance in yellow is the exact same as this distance in blue? No. I don't like that. How could I draw this picture so that all three of them are equal? Yes.
An equilateral triangle.
Oh, if I put them in a triangle. Boom, boom, boom. A, B, and C. AB congruent to BC, congruent to AC. Equilateral triangle. Okay. Does that satisfy the beginning portion?
Yes.
Does that satisfy this? Absolutely. However, are they collinear? No. So this is false. And our counterexample is that A, B, and C are vertices of an equilateral triangle. This entire unit, the question was, can we just put equal triangle? No, equilateral is an important vocabulary word. I know we haven't actually talked about triangles later, but we will get that one in like 3 units from now. Also, let's be careful with just shortening things. This entire unit is going to be more writing intensive than other sections of the entire course. All right. AB plus BC equals AC. By the way, what's it mean when there is no symbol above it? It's not just points. Come on, y'all. We covered this. There's a difference between this and that. What's the difference in the two? One's the line segment or the line or whatever, the geometric construct. The one below it is just the length, the measurement, distance between them. So if the distance from A to B plus the distance from B to C equals AC, so let's draw that. A, B, and C. So then AB equals BC. Well, in this one that I've drawn, is it true that AB plus BC, so AB plus BC equals AC. Is that true? Yes. So does it conclude then that AB equals BC? Those two distances are the same. Yeah? Only when there's a midpoint, right? So it could be that this was 3, this was 8, and the whole thing is 11. So AB equals 3, BC equals 8, AC equals 11. So AB plus BC equals AC. That checks off. Because here, AB is 3. That's what I got right there. BC is 8. That's there. AC is 11 is the whole thing. I'm giving an example. I'm making it up. I'm saying, is there some example out there that makes this true? And it only takes one. So I made one. All right? AB plus BC equals AC? Yes. AB equals BC? No. Therefore, this guy is false. And this entire scenario here is my counter example. Okay? Very example. It's a situation that can occur where the original condition is met, the second one is not.
So basically, we just have to solve that and decide if it's true or false.
In this particular scenario, yes. You're just telling me true or false.
So what's the difference between the with the line and without the line?
The with the line is the actual line segment, is this physical piece. The other one is the measure. The distance between. All right. If angle 1 is complementary to angle 2, and angle 1 is complementary to angle 3, then angle 2 is congruent to angle 3. Yeah. True? It sounds true. Might be false. Here's what I'm going to do. What does complementary mean? Well, wait, it's what? Two angles that add to, sum to be 90 degrees. Okay, so here's what that means. Measure of angle 1 plus the measure of angle 2 equals 90, right? Now, we also know that the measure of angle 1 plus the measure of angle 3 is equal to 90. That comes from the second half of that, right? Now, since they both equal 90, doesn't that mean that measure of angle 1 plus measure of angle 2 must equal this one, measure of angle 1 plus measure of angle 3? So I'm going to set those equal to each other. Measure of angle 1 plus measure of angle 2 equals measure of angle 1 plus measure of angle 3. Y'all with me so far?
Yes.
All right. Now, I'm going to use one of my properties of mathematics and say that if I subtract something on the left, I must also subtract it on the right. Those two subtract out, leaving me with measure of angle 2 equals measure of angle 3. Now, notice what I've done here. I have not used any specific numerical examples. I have not said, well, if measure of angle 1 is 10 and measure of angle 2 is 80, I haven't done any of that sort of stuff creating examples. I've shown from base root logic using mathematical notation and mathematical processes that given this condition, then this logically follows from it. This is the very first rudimentary example of a thing that we're going to call a proof later on. Now, we're going to flesh it out a whole lot more. It's going to look different. It's going to have more parts to it to help you guys stay organized. But this is the kind of thing that we're doing for a proof. Okay? This would not get you credit on an assignment. Okay? This is just a very early example of it to determine truth or false, or true or false. But we will be getting to stuff like this later on. That is true. Yes? Is a proof like an essay? It can be. There are different ways of doing it. And we'll talk about those. There's double column proofs, there's paragraph proofs, there's flowchart proofs, there's all sorts of stuff like that. Okay. Back to some more definitions. All right, a conditional statement is a statement that can be worded in if-then format. And this example about Tuesday and Wednesday we're going to be using all the way through for the next few examples. If today is Tuesday, then tomorrow is Wednesday. All right? I realize that as I'm saying this right now, it is a Friday. Don't get hung up on that, all right?
Today is Friday, tomorrow's Saturday.
Yes, that is true. However, notice that word if. If today is Tuesday, then tomorrow is Wednesday. True or false? True. All right, I like that. All right, now, the hypothesis, and I told you I would be using this word slightly differently than you have in your science classes. It's just the if part of the conditional statement, okay? So that is the if today is Tuesday. And I'm using blue for my hypothesis on all these, all right? So you can actually visually see this. Also, my conclusion is the then portion, and I'll be doing that in orange. So there's my blue and there's my orange. Just to color code those. Conclusion is the then portion of the conditional statement. If then. All right, questions on that? All right, simple definitions. All right, so now, negation is when you change a statement from a positive to a negative or from a negative to a positive. So, in this situation, we got not. The negation of today is not Tuesday. Now, we got to be careful with negations because when we say we're using a negative, we're kind of like including everything else that wasn't included before. So, for example, today is Tuesday is which day of the week? Tuesday. Not Tuesday is Sunday, Monday, Wednesday, Thursday, Friday, Saturday. All the others. Now, we got to be careful with that with words. Like typical and atypical are exact opposites of each other because the prefix a is a direct contradiction, right? It's a direct negation. We got to be worried about words like, honestly, positive. What's the negation of positive? Negative. We want to say negative, but let's look at the number line. -3, -2, -1, 0, 1, 2, 3. All right, here are all of our positives, right? And it goes on forever. Just like that whole Tuesday versus everything else, the negation of positive needs to include everything else. And if I say just the word negative, I'm including only those. That is not a true negation because I left something out. I left out 0. So a true negation would be all of these things. So the negation of the word positive is actually non-positive or not positive. Okay? My point is be careful with that so that whenever you use a negation, you're actually getting everything else. There's a difference between negative and non-positive. Negative starts, if we're just looking at integers, starts at -1 and keeps going down. All of these guys here. Non-positive also includes 0 because 0 is non-positive. 0 is neither positive nor negative. So we got to say non-positive to get 0 in there. Okay, we'll get better at that. Just be careful. All right, converse is where, let me remember my colors here. Okay. We switch the if and the then portions. So notice how today is Tuesday went to the back and tomorrow is Wednesday is now at the front. We just switched our if and then. Swap or exchange the hypothesis and the conclusion. And no, converse is not a shoe with a star on it in math class. All right, we okay with that? Just swap them. Easy enough. Oh, sorry. Give you all a chance to write. All right. Now, the term biconditional is when a conditional statement and its converse are both true. Now, we've already listed these two off about If today is Tuesday, then tomorrow is Wednesday. We already said that was true. What about the converse? If tomorrow was Wednesday, then today is Tuesday. Is that also true? Yes. If they are both true, then it is a biconditional. Now, one of the ways that biconditionals can be phrased is with the phrase if and only if. And that's a lot to write, so you'll see me abbreviate that with IFF. And that gets placed in the middle. Today is Tuesday if and only if tomorrow is Wednesday. That implies that conditions go both directions. All right. All right, y'all, we're making good time. Okay, I'm going to skip contrapositive and come back to it. So you'll have time to write that when we come back to it. I'm going to do inverse first. The inverse is when you negate the hypothesis. So if today is not Tuesday, notice that my Tuesday is still first. My Wednesday is still second, but I've got the nots on there. Not Tuesday, then tomorrow is not Wednesday. And our truth value is determining whether or not something is true or false. Man, there must be allergies going around today. I've had people sneezing all day long. And don't you know it's awesome that all those sneezes and nose blows are preserved forever on YouTube? That's amazing. Only saving the best things in life on this station. All right. Okay, we're going to jump back to contrapositive now. Now, a contrapositive is a funny sounding word, but it's when you negate the hypothesis and conclusion of the converse. So, notice on this one, Wednesday comes first, Tuesday, wrong color. Tuesday comes second, and they both have the knots on them. So basically, a contrapositive can be thought of as the inverse of the converse or the converse of the inverse. Basically, you just do both. Switch them and negate them, and you got contrapositive. Now, contrapositives become very important the higher up you go into various fields of mathematics when you're doing different kinds of proofs. They're not as important here in basic geometry, but we got to go ahead and cover them so you hear that word if you ever need it. Okay. I believe that's the last of our definitions. We're just looking at examples from here on out. And truth value, we talked about that, truth or false value of a statement. All right. Now, when we're doing this when we're doing examples trying to create a hypothesis and conclusion and write an if-then form, anytime we have like a scenario, like a real world type scenario that's not mathematical, sometimes you got to do some wordsmithing to make this whole thing work out. So just do the best you can with fitting these together. So get a free water bottle with a 1-year gym membership. First off, what's the hypothesis and what's the conclusion? Go.
Hypothesis is that you'll join the 1-year gym membership.
Okay, the hypothesis is the gym membership. And why would we not say the hypothesis is the free water bottle?
If you get a free water bottle.
There's like a result.
Okay, yeah, like a cause-effect relationship. Yeah. So it wouldn't be kind of weird to say that if you got a free water bottle, then you will get a 1-year gym membership. Like you're walking down the road, pick up a water bottle off the street, and somehow you got a gym membership. Yeah, that would be awesome. Okay.
That's how coupons work.
That's how coupons work. Okay. So if you, and I said some word membership here, but I'm going to go ahead and use, wordsmithing. I'm going to go ahead and put the word buy in there, even though it doesn't occur, because if you buy a 1-year gym membership, then you get a free water bottle. And the reason I say buy is a fair assertion there is because, I mean, that's the way these things work, that you buy a membership, and by purchasing their product, they give you something else for free of lesser value. Where you buy the $50 gym membership per month and they give you a $2 water bottle for free, not the other way around.
It would be awesome if it could be the other way around.
Yeah, it'd be awesome if you got a $2 water bottle and then they give you like a 1-year gym membership, so that's what, 50 times 12 is $600 value for a $2 water bottle. Yes, let's do it. I'll tell you what, you open that gym and tell me if it works out financially for you.
I'm going to be bankrupt before I even start.
Yeah, bankrupt before you open the doors the first day. Okay. All right, example 11. We're going to identify our hypothesis and conclusion. Adjacent angles have a common side. Now notice this is not a real-world scenario. This is a mathematical scenario. So in this one, we don't have to do as much wordsmithing or figuring out cause and effect so much. We kind of take them the way they come. So our hypothesis here is our adjacent angles, and the conclusion is the common side. So if, now how would I write that? If, okay, if, we want to try to stay away from the if you have, or no, we always want ifs, but we want to stay away from the you have scenario. Because technically I don't have it. If an angle, or if angles are adjacent, we're talking about the properties of the angles. I'm sorry, what did you say?
If the angles are adjacent, then you'll have a common side.
And again, stay away from the you'll have. Don't use the you have. So if angles are adjacent, then they have a common side. And notice what I did here about they have versus you have, because I don't share a side with an angle. The two angles share with each other. Yes, sir?
This one will biconditional,
Yeah, that's what I thought.
If angles have a common side, then they are
adjacent.
adjacent. Possibly. Let's test it. So the side of an angle is the ray of it, right? What if I did this? Do angle 1 and angle 2 share a common side? Now, you would argue there about whether or not the side starts here or starts there, but this is the type of outside cases or edge cases you got to consider, okay? My opinion, it would be a biconditional, because in my opinion, like if I label these A, B, C, D, and E, then in this case, the side of angle 2 is actually EB, ray EB, whereas the side of angle 1 is DB. Therefore, that's not exactly the same side. So that's not a common side. So this doesn't really apply. But my point is, you got to look at those weird edge cases. Okay? All right, next up. All apes love bananas. And this is where you get some interesting, weird ways of saying this stuff. First off, hypothesis. Okay, hypothesis is basically something's an ape, right? The conclusion is loving bananas. And I don't want to say if I have an ape, because I really don't want an ape. And who owns the ape is irrelevant here, right?
If an ape exists, it loves bananas.
Okay, the way I write it is if an animal is an ape, one of my students just said, if an ape exists, I think that would be acceptable. Then it loves Bananas. One thing I hear quite frequently, thankfully nobody in this particular class said it, was they'll say things like if it is an ape, and go on from there. I don't like that. The reason I don't is because you're saying it before you identified what it is. Where we don't like to use pronouns before we've identified it with a noun. Sir?
What about if there is an ape?
If there is an ape, then it, like those bananas, I guess that would technically work too. But yeah, just stay away from using it before you've defined what it is. It's like walking into the room and said, hey, did you hear what he did? What's the next question? Who's he? They want you to define the pronoun. Okay. Collinear points lie on the same line. What's our hypothesis? Collinear points, and then lie on the same line. So, if there is collinear, okay, I know we can get weird here, right? If points are collinear, then they lie on the same line. And again, like I said, careful with pronouns. The reason that they is all right here is because we already defined what they is, right? It's the points. You what? If points lie on the same line and they are collinear, yes, this would be a biconditional. Because the converse is also true. If points lie on the same line, then they are collinear. All right? 13. Those who do not remember the past are condemned to repeat it. What's our hypothesis? Okay, those who do not remember the past. And then people are condemned to repeat it. So, if a person does not remember, horrible M, the past, then he, she, they, what's the proper word there now? It. They are condemned to repeat it. This, I mean, I know this is considered acceptable. It kind of, I got issues with it sounding right to me because we're talking about a single person but plural. But you're talking about a single person out of many, and I don't know. This is why I'm a math teacher. I can do some basic grammar, but beyond that, I get confused. Okay. A few more examples here, and then we're done. Here we're going to be writing the converse, inverse, and contrapositive, and also determining whether or not it's a biconditional. So, first off, if you are a teenager, then you are at least 13 years old. True or false? Oh, I heard one person here say false. Can you give me a counter example? Okay, so someone says if you are 20, so a 20-year-old. Now my next question is, does this satisfy the hypothesis? Because in order to be a counter example, it must satisfy the hypothesis but contradict the conclusion. So, does this fit into the teenager category? No. Therefore, we cannot consider it for a counterexample. Okay? So what are the only ages we're allowed to use here? 13 through 19. And in every case, are those at least 13 years old?
Yes.
Yes. So this one is true. All right, now, converse. I'm going to abandon my blue and orange highlighters here because I think we've got it down now. Converse is if you are, what do I do for converse? Negate or flop? Look back if you don't remember. Yeah, we switch them, so we flop them. So if you are, Well, we're going to take this and put it to the beginning. So if you are at least 13 years old, then you are a teenager. I'm just going to write teen. Now, true or false?
True.
True? Anybody want to say false? No? I do.
Oh yeah, yes, because that's counting all the ages above.
Yeah, because again, forget what was going on up here. Okay? We are going to look only at this statement. Look at the conclusion or the hypothesis. If you were at least 13 years old, what ages does that include? 13 plus all the way up to infinity, or till the oldest person's age, right? In particular, for a counterexample, we need a specific one. Let's use a 20-year-old. Does a 20-year-old satisfy this hypothesis? No. Whoa. Does it satisfy this hypothesis if you are at least 13 years old? Yes. Now, if you're 20, then you are a teen. Is that true? No. So this one here is false. Therefore, it is not a biconditional. The most tempting thing to do here is to say that my condition or my example for the converse satisfies the condition of the hypothesis of the original. Don't do that. Separate sets of counterexamples, okay? All right, now my inverse, I'm throwing my knots on there.
If you are not at least 13.
Careful, it's inverse of the original. So if you are not a teen, then you are not at least 13 years old. And I'm not going to worry about truth values on those. But contrapositive, negate the converse. If you are, and we're going to look here, if you are not at least 13 years old, then you are not a teen. Or more properly, a teenager. All right. 16. Oh, this is a fun one. It'll be even more fun when people are listening to it on YouTube because different states have different laws. All right, we're assuming in Texas here. At Texas, you can get a provisional driver's license at 16. You can get a learner's permit at 15, provided you meet all the requirements, courses, all that sort of stuff. So, if you have a driver's license, you are at least 16 years old. First off, in general, is that true? Yes. Are there any counterexamples? Yes. Oh, I see some hands. Go.
If you are at least 16 years old, then you have a driver's license.
I'm looking for, not the converse, I'm looking for, is this true? No. Can I have a counterexample to this? Yeah. Or is there someone who has a driver's license who is not at least 16 years old? Wow. Okay, go.
So my cousin, his mom can't drive and he's 15, so it's a special thing where he has a driver's license.
Let me repeat that. He says that his mother, by the way, this is still in Texas, his mother has a disability, can't drive, he's 15 years old, satisfied all the other conditions of getting a license, and they issued him a license at 15 years old. That is called in Texas a hardship license. So we have a 15-year-old with a full driver's license. I say full. There's different conditions, but it is a driver's license where you can drive without anyone else in the car. There's my counterexample. Therefore, this is false. And the sad part is, whenever we wrote this, We intended that to be a true statement, but whatever. Hey. Well, you don't think about those edge cases, right? Yeah, you should. You're right. You should. Shame on me. But at least I'm a big enough man to admit that I was wrong, and I will let this be the correct answer. Okay. Converse. By the way, just for information's sake, the only time that I've heard of the hardship license actually happening are that disabled parent. I've heard of weird cases. I don't know if these are verified as true, but like the oldest child in a very large family, and all the children could not fit in one car, so they needed an additional car to be driven. Okay. I've also heard of someone who was working a full-time job to help support the family in a very poor family. I've heard of all those scenarios happening. Anyway, moving on. Converse. All right, so converse. We're going to switch the hypothesis and conclusion. So if you are at least 16 years old, then you have a driver's license. By the way, I'm not even going to ask if this is true or false, because for the biconditional question, as soon as this one was false, the answer is automatically no. If either one is false, it is not a biconditional. Which, by the way, but just for kicks, is that true?
No.
If you are at least 16, then you have a driver's license? No, my autistic friend proves that one wrong, right? He's 30 years old and does not have a license, right? Never wanted one, right? Okay. Inverse. If you don't have a driver's license, then you are not at least 16 years old. Okay, what was the question? All right, never mind. Okay. Contrapositive. If you are not at least 16 years old, then you don't have a driver's license. All right. More writing in this unit, but overall not as difficult as some of the stuff we did last unit as far as solving and things. Okay, if you're still writing, I apologize. I've got to move on. I can let you copy these down at the end of class or after school or something. Okay, so again, write the converse, inverse, same stuff as before. Okay, if 2x plus 6 equals 10, then x equals 2. First off, is that true or false?
True, but it can be false.
It can be false? How?
You can put it as a fraction.
But what is a fraction?
You can put it as
Well, you're saying it. I don't know what it is.
it. You can put 2 as a fraction.
2 over 1. But if you, it's still going to be true, though.
So you can put 2 over, no, 4 over 2.
So we make it 4 over 2. So if we do 2 times 4 over 2 plus 6, that's still going to come out to 10. Yeah, right. So it's written different ways, but it's still true. No, this guy is absolutely 100% true. All right, converse. If x equals 2, then 2x plus 6 equals 10. Is that true? Yes, it is. This is also true, therefore my biconditional is satisfied. It is a biconditional. All right, inverse is a lot easier to do on this one. If 2x plus 6 is not equal, is not equal to 10, then x is not equal to 2. Equal marks are very easy to negate. You just put a slash on them. And then my contrapositive, if x is not equal to 2, then 2x plus 6 is not equal to 10. All right, so I'm going to go ahead and cut the video. For all those on YouTube, thank you for joining in. Tune in next time. And as always, please stay patriotic.